if an arithmetic sequence goes up by the same amount, adding and subtracting, a geometric sequence goes up or down with multiplication. So in that case, we have a common ratio. So all geometric sequences have common ratio. So to find the common ratio means divide. You're going to take the second term and divide it by the first term. So I'm going to use the notation of A's and subscripts. Sometimes with geometric ratios, you can have a different letter, such as G for geometric. I'm going to stick with the A's. So A sub 2 means the second term, A sub 1 equals the first term, and A sub n equals the nth term. So in an explicit formula for a geometric sequence, you have A sub n equals the first term times the common ratio to the n minus 1 power. So n minus 1 is a superscript, so that means it's an exponent. This r I often put in parentheses, and I'll put r in parentheses if the number is a decimal, a negative, or in a fraction. But you need to have it in parentheses if it's a negative in a fraction, because it makes a difference with your exponent. And again, we also have a recursive formula. So the recursive formula is you take, again, you have A sub 1 equals A sub 1, just like the arithmetic. And then you have A sub n equals A sub n minus 1 times r. Okay, so if you remember for the arithmetic, you had to add the d because the d was the common difference. Now we're multiplying by the r, which is the common ratio. So you're going to have to fill in, when you're writing an equation, the A sub 1 and the r for both of these. So first one, identify whether the sequence is arithmetic, geometric, or neither. If it is geometric, identify the common ratio. So on this one, what I'm doing is I'm looking and I'm noticing that it's going from positive to negative to positive to negative. In that case, it will never be arithmetic because either all the numbers will decrease or all the numbers will increase if it's arithmetic, and increase and decrease by the same number. So to check geometric, what you need to do is divide negative 216 by 36, and I get negative 6. And I divide 36 by negative 6, and I get negative 36. Negative 6 divided by 1 is negative 6. So all of these are the same, which is negative 6. So the common ratio is negative 6. So it is geometric. Okay, number 2. I can see right away that we're just adding 2. So it is arithmetic with a common difference of 2. Number 3, again, it's going positive, negative, positive, negative. So it can't be arithmetic. So I'm going to divide these two, and I get negative 4. Divide these two, this third term divided by the second term, and I get negative 4. Second term divided by first term, and I get negative 4. So it's geometric. And your r equals negative 4. Number 4, it looks like the numbers are this is going up by 3, this is going up by 5, this is going up by 7, it's going to go up by 9. But it's not going by the same amount every time. For it to be arithmetic, it'd have to increase by the same amount, and it's not. So it's neither. And then number 5, 6, and 7 deal with finding the missing term of a geometric sequence. That is finding the geometric mean. So to find the geometric mean, what you need to do is you need to multiply the two numbers. So I'll call this number A sub n, and then A sub n plus 2, okay? Because that means it's not the next term, it's the second term after that term. So you take the square root of them after you multiply them. So this first one, number 6, then I'll go back and do number 5. So number 6, to find the missing term, it's going to be 20 times 80 the square root. So I'm going to multiply 20 times 80, and I get 1,600. So the square root of 1,600 is 40. But in a geometric sequence, I can't tell if it goes positive, 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 or the R could be negative, and it could go positive, negative, positive, negative. So I'm going to need to write plus or minus on this. Okay, for number 7, I'm going to do the same thing. I'm going to take the square root of 3 times 18.57. And I have to round, so it's approximately plus or minus 7.46. And number 8, I can't tell if the R is negative or positive, so it's going to be 28 times 5103, and then take the square root of that. So it's plus or minus 378. Okay, now I'm going to look at number 5. So a family purchased a home for $150,000. So this is year 1, $150,000. 2 years later, the home was valued, it's kind of weird, at $188,160. If the value of the home is increasing geometrically, how much was the home worth after 1 year? So you don't know what that house was worth in between those two, but it's increasing geometrically. That just means that it's increasing by a percent. So what you're going to do, because a percent would be the common ratio, so if something was increasing by 10%, the common ratio would be 1.10. So I'm going to multiply 150,000 times 188,160, and then take the square root of it. And I get 168,000, because I want to write it with money, even. Okay, so I wouldn't do plus or minus on this because I can't have a negative. It won't be negative in between there. Okay, we were talking about prices of homes. Okay, 9 and 10. You want to find the 19th term of the sequence. So just to practice this, I'm going to write the explicit formula and the recursive one. So the explicit formula and recursive one, I need the first term, which is 11, and I need the R, which is 3. So my explicit formula is going to be A sub n equals the first term, which is 11, plus, well, actually, this is, I got to erase that, plus, because we're talking about the geometric sequence, not the arithmetic. So it's going to be 11 times 3 to the n minus 1. Whereas the recursive formula, you need to do 2 lines. So the a sub 1 equals a sub 1. A sub 1 is 11. And then a sub n equals the previous term times r, which is 3. Oops, that's multiply. So again, the recursive formula has 2 lines. Explicit is 1. You want to use the explicit formula if you have to find a higher terms, because otherwise the recursive formula right here would be 11 times 3 is 33, times 3 is 99, times 3 is 297, times 3, 297 times 3 is 891, times 3. You'd have to keep going until you got to the 19th number, which could take a lot. But in the explicit formula, you can just plug in 19. So it's 11 times 3 to the 19 minus 1, which is 18th power. So this is going to be a huge number. So I might have to use scientific notation. Nope, I don't. So it's 4261625 Okay. Excuse me. So it's 4,261,625,379. All right, 19th term in this one. So if you're looking at this one, this is geometric because we're multiplying by 3. This one is arithmetic. So I'm going to do just the explicit formula for the arithmetic sequence. I could write the recursive formula too. I know I'm not going to use that. So this is going to be a sub n equals a sub 1, which is 20, plus n minus 1 times the difference, which is a negative 3 because you're going down 3. So to find the 65th term, or 19th term, I'm just going to write in 19 for n. So it's 20 plus 19 minus 1 times negative 3. So the 19th term is 20 plus the quantity 19 minus 1 times negative 3. And you get negative 34. So the 19th term is negative 34. Okay, number 11. Suppose you have an equipment that can enlarge a photo to 120% of its original size. A photo has a length of 10 centimeters. Find the length of the photo after 5 enlargements. I'm going to write this sequence out. So the first length is 10 centimeters. So after 1 enlargement means that if it's 120% of its original size, the common ratio is going to be 1.2, because 120% as a decimal is 1.2. So I do 10 times 1.2, and I get 12. So that's after the first enlargement. Then I enlarge it again. So 12 times 1.2 is 14.4 centimeters. Then I times it by 1.2 again. So that's 17.28. So after the fourth enlargement, it's going to be 20.736. So it went 1 enlargement, 2 enlargement, 3 enlargement, 4 enlargement. So I need to multiply it one more time by 1.2. And I get exactly 24.8832 centimeters. So I'm going to try this with using an explicit formula, and I'm going to see if it works. So the explicit formula would be a sub n, so it'd be the a sub n equals 10 times 1.2 to the n minus 1. So if I plugged in, the reason I didn't use the explicit formula, or if you do, you have to really pay attention to how you're using it, is if you write n equals 1, to me that means after 1 enlargement. So after the first enlargement. So let's plug in 1. What do we get? So we're going to get 10 times 1.2 to the 0 power. Well, 1.2 to the 0 power is going to be 1. So after 1 enlargement, you'd get 10. So that means that the first term is 10. So that doesn't make sense. Because if you're enlarging it, it would be bigger after 1 enlargement than 10. So then if you're going to use this formula, you'd actually have to start with the first enlargement being n equals 2. Okay, so that means that if you're trying to find 5 enlargements, you would plug in not n equals 5, but you'd plug in n equals 6 to this formula. So sometimes when I'm doing these sequences with the explicit formula, I have to pay attention to the wording, and it's after 5 enlargements, so I have to figure out if I plug in 1 to the explicit formula, does it make sense?